Good afternoon, everyone. My name is Arif Hasan. I am an assistant research professor at the University of Arizona. Today, I will present some of our recent research progress on the concept of mechanical elastic pseudo-spin that exhibits coherent superpositions of elastic states in an acoustic waveguide, which is analogous to a superposition of spin states. Hence, we refer to it as pseudo-spin. Then I will focus on the concept of non-separability of sound wave, which is analogous to quantum entanglement. This work is done in collaboration with Professors Lazare Calderin, Pierre Luca, Keith Runge, and Pierre Demier at the University of Arizona. To begin with, let me show first how broken symmetry and therefore non-conventional topology leads to a half-integer spin analog or pseudo-spin in an elastic system. And let's take the example of an intrinsic topological phononic structure as shown here. In the limit of long wavelength, the governing equations of motion of the coupled waveguide can be written as such. In this equation, M2 by 2 is a coupling matrix. This equation takes a form similar to Klein-Gordon equation. Using an approach paralleling that of Dirac, we can factor the Klein-Gordon equation as such. In this Dirac equation, U2 by 2 and U4 by 4 are anti-diagonal matrices with unit elements, and sigma 1 and sigma 2 are the two Pauli matrices. And finally, C4 by 1 is a four-dimensional vector that represents the modes of vibrations of the coupled waveguides projected in the two possible directions of propagation. Now let's focus on the Dirac equation again. In this equation, if we change the time t to minus t, the equation changes. Hence, the time reversal symmetry is broken. Moreover, if we change the position x to minus x only, the equation again changes. Therefore, the parity symmetry is also broken separately. Now let's seek the solution of the Dirac equation in the form of plane wave as such, which gives the two dispersion relations as shown here, as shown in the figure. The first set of dispersion relations, the red solid line, goes through the origin and it relates to symmetric eigenmode. For such case, let's assume the amplitude of the plane wave as such. Let's assume the amplitude of the plane wave A1 equal to A2 equal to AF, where AF is the forward component of wave, and let's assume the amplitude A3 equal to A4 equal to AB, where AB is the backward component of wave. Hence, we obtained the following eigenvalue solution, which are satisfied by the plane waves of arbitrary amplitudes. Hence, for the case of first dispersion relation that goes through the origin, the displacement of waves in the forward and backward directions are not related to each other. On the other hand, the second set of dispersion relations, the blue solid line, has a cutoff frequency and it relates to the antisymmetric eigenmode. For such case, let's assume the amplitude of the plane wave as such. Let's assume A1 equal to minus A2 equal to AF, and let's assume the amplitude A3 equal to minus A4 equal to AB. Hence, we obtain the following eigenvalue solution, which are satisfied by the plane waves of constant amplitudes. Therefore, the displacement of waves in the forward and backward directions are not independent of each other. Hence, the second dispersion relation in the band structure is associated with a wave function whose amplitude shows spinor character, that is, the spin-like states in the direction of propagation, since the displacement of waves in the forward and backward directions are constrained. Therefore, for such non-trivial eigenvector, we can write the plane wave solutions as such, as a tensor product of the eigenvector of the coupling matrix and the spinor. Moreover, the eigenvector of the coupling matrix is analogous to the orbital angular momentum degrees of freedom, and the spinor components represents the amplitudes of the quasi-standing waves propagating in opposite directions along the waveguides. To physically realize an elastic system that exhibit pseudo-spin characteristics, we have fabricated coupled acoustic waveguides. that consist of aluminum rods which are glued along their length with epoxy and with almost fixed lateral gap of 2 mm. We have fabricated coupled 2 rods, coupled 3 rods and coupled 4 rod acoustic waveguides. This figure shows one of the experimental setup of our system that consists coupled 3 rod acoustic waveguides. In the experiment, a set of transducers are used to drive the rods at one end. Another set of transducers are also used as detectors. The driving transducers are connected through the signal generator to drive the rods with sine waves with a scan in frequency between 1 kHz until 100 kHz in steps of 50 Hz. The detecting transducers are connected to the oscilloscope and then to the computer to record the transmission, which is averaged over 256 times. First, I will show the experimental results for coupled 2-rod acoustic waveguides. For the case of coupled 2-rod waveguides, there are two eigenmodes of oscillations, symmetric 1-1 and antisymmetric 1-1. Hence, in the experiment, we drive the coupled waveguides with amplitude corresponds to symmetric mode of stimulation as well as antisymmetric mode of stimulation as such, and we obtain these experimental results. This figure shows the experimental transmission spectrum of the coupled 2-rod waveguides, where x-axis is the scanning frequency from 1 kHz until 60 kHz and y-axis is the transmission amplitude in arbitrary units. And the red solid line corresponds to the transmission amplitude for symmetric mode of stimulation, and the blue solid line corresponds to the transmission amplitude of antisymmetric mode of stimulation. From this figure, it is clear that the transmissions are dependent on the mode of stimulation. For the case of antisymmetric mode, we can clearly see in the blue lines a large depression in the transmission amplitude, say around 20 kHz. Moreover, the peak positions in this plot defines the resonance frequency of the standing wave mode with either uniform frequency spacing for the case of symmetric mode of stimulation or non-uniform frequency spacing for the case of antisymmetric mode of stimulation. The wavelength and hence the wave number associated with such standing wave mode can be easily calculated through this expression by knowing the length of the acoustic waveguides. Finally, by calculating the resonance frequency and the wave number, we obtain this experimental band structure for the coupled 2-rod waveguides. In this plot, the x-axis is the wave number and the y-axis is the resonance frequency, and the asterisks are obtained from the resonance frequency of the symmetric mode of stimulation, and the solid line associated with the asterisk is a feet, which gives the speed of sound of the nearly one-dimensional acoustic waveguides. And the open circles are the resonances obtained from the antisymmetric mode of stimulation, and the solid line associated with the asterisk with the open circle is a feet of the dispersion relation, which gives the cutoff frequency of around 20 kHz. If you recall, as I mentioned before, the dispersion relation with cutoff frequency represents states which are analogous. The dispersion relation with cutoff frequency represents states which are coherent superpositions of elastic waves propagating in opposite directions along the waveguides, which is analogous to a superposition of spin states. Hence, the presence of the cutoff frequency in the band structure is a signature of elastic pseudospin for the case of coupled 2-rod waveguides. Next, I will focus on the experimental results for coupled 3-rod waveguides. Similarly as before, for the case of coupled 3-rod waveguides, we drive the waveguides with amplitudes corresponds to each of the orbital angular momentum degrees of freedom 1, 1, 1, 1, 0, -1 and 1, -2, 1. And we obtained this experimental transmission spectrum for the case of coupled 3-rod waveguides. By calculating by calculating the resonance frequency and the associated wave number, we obtained this experimental band structure for the case of coupled 3-rod waveguides. From this figure, we see that for the case of coupled 3-rod waveguides, the orbital angular momentum has two mutually orthogonal states with cutoff frequency in the band structure. And as I mentioned before, the dispersion relation with cutoff frequency represents pseudo-spin states. Hence, the presence of the cutoff frequency is the signature of elastic pseudo-spin. And moreover, from the two mutually orthogonal states, the orbital angular momentums, we have shown that we have experimentally obtained a two-level classical analog of a qubit, what we call phi bit. Therefore, a phi bit is a one-dimensional elastic system that exhibits a superposition of two mutually orthogonal states. Now let's recall the theory again. As I mentioned before, using an approach paralleling that of Dirac, we can factor the time-coded equation as such. Here I am showing the Dirac equation for the coupled 3-rod waveguides. Since the Dirac equation is linear, any superposition of modes is also a solution. Therefore, let's write the linear combination of isofrequency states as such. In this equation, n and n prime corresponds to two pseudo-spin bands in the band structure for the case of coupled 3-rod waveguides. And we have assumed isofrequency states, hence the frequency in the two bands are the same. By writing such, we are able to create an elastic waves which are non-separable superposition of isofrequency states. Since such superposition of states cannot be written in the form of a tensor product of one orbital angular momentum eigenvector and one spinor, since both the eigenvectors of the orbital angular momentum degrees of freedom and the spinors are different. Such non-separable superposition of isofrequency states are analogous to Bell state of quantum mechanics. To physically realize such non-separable superposition of elastic states, that is the Bell state, we need to find the isofrequency state in the experimental transmission spectrum for the coupled 3-rod waveguides. If I zoom in the regime between 30 to 35 kHz of the experimental transmission spectrum, we see that for the isofrequency value of 33.25 kHz, there is substantial transmission of OM2 and OM3, the blue and the green solid line, and at the same time there is very little transmission of the OM1. Therefore, to create a non-separable state in the experiment, we drive the rods with a frequency of 33.25 kHz by exciting rod 1 and rod 2 out of phase. We also manipulate the excitation amplitude of the two rods by the parameter R through this expression. In the experiment, we drive the rods for different values of R and we obtain these experimental results. In the top figure, I am showing the transmission amplitude of each of the rods as a function of the excitation amplitude ratio R. And in the bottom figure, I am showing the variations of the phase difference between each pair of the rods, again as a function of the excitation amplitude ratio R. From this two plot, we see that by manipulating only one parameter, which is the excitation amplitude ratio, we can tune the eigenmode superposition, which means that first, by exciting a particular isofrequency state to drive the system, we are able to create a superposition of mutually orthogonal elastic states which are non-separable as such. So here we are able to create a non-separable two phi bits. The first phi bit being the orbital angular momentum degrees of freedom, and the second phi bit being the pseudo-spin states labeled by the wave number k. And then to control the coefficients of such non-separable states A and B, we drive the rods for different values of R, which is the excitation amplitude ratio, which eventually manipulates the transmission amplitude of each of the rods as well as the phase difference between the rods through this expression. Moreover, from this equation we see that the coefficients A and B of the such non-separable states, that is the Bell states coefficient, must be complex. Hence, finally, first by choosing an isofrequency state, we create a non-separable state, and then by tuning the excitation amplitude ratio, we are able to tune the complex coefficients of the Bell state, which means that we are able to navigate the Bell state's Hilbert space experimentally. We have also calculated the entropy of entanglement, and for a particular value of R equal to 1, we have achieved maximally entangled state. Next, To study high-dimensional non-separable states, we have created coupled forward waveguides. And similarly as before, from the experimental transmission spectrum, we construct this band structure for the coupled forward waveguides. And again, in this plot, x-axis is the wave number and y-axis is the resonance frequency. From this plot, we see that for the case of coupled forward waveguides, the orbital angular momentum has three mutually orthogonal states, OM2, 3 and 4, with cutoff frequency in the band structure. And as I mentioned before, the dispersion relation with cutoff frequency represents pseudo-spin states. Hence, we have experimentally achieved a three-level classical analog of a Q-DIT, what we call phi-trit. And again, a phi-trit is a one-dimensional elastic system that exhibits a superposition of three mutually orthogonal elastic states. Next, for the case of finite length waveguides, the wave number space are discrete. We can select a three pseudo-spin states with labels as such, associated with the corresponding wave numbers K2, K3 and K4 to realize a second phi-trit. Therefore, by choosing a particular isofrequency state, we are able to create acoustic non-separable states of two phi-trit. And again, the first phi-trit being the orbital angular momentum degrees of freedom and the second phi-trit being the pseudo-spin states labeled by the wave number K. Next, again to tune the non-separable states for the case of coupled forward waveguides, which means to navigate the Bell-Hilbert space, we excite the coupled waveguides with an external force as such through this expression. From this equation, we see that by manipulating the value alpha, the contribution of the linear combinations of the three eigenmodes superpositions OM2 and 3 and 4 can be experimentally manipulated through this expression. Since we see that when alpha equal to 0, from this equation we see that the output mode should be a pure eigenmode of OM4, and when alpha equal to 1, the eigenmode should be pure of OM3, and alpha equal to 0.5 should be a state of two non-separable phi bits. And finally, for all other alpha values, the state should be a two non-separable phi-trits, and the first phi-trit being the orbital angular momentum degrees of freedom and with corresponding pseudo-spin labels K2, K3 and K4. In the experiment, we choose different alpha values to excite the rods externally, and we achieved this experimental figure. This plot shows the variations of the phase difference between each pair of the rods, rod 1 and rod 2, rod 2 and rod 3, and rod 3 and rod 4, with a function of alpha. From this plot, we indeed see that by manipulating the value alpha, we can tune the eigenmode superpositions. For example, when alpha equal to 0, we experimentally obtain the phase difference between rod 1 and rod 2, rod 3 and rod 4, and between rod 1 and rod 2 and rod 2 and rod 3 and rod 3 and rod 4, all of them are almost equal to pi, 180 degree, which means that for alpha equal to 0, the output mode of vibration is almost purely OM4. And when alpha equal to 1, we experimentally obtain the phase difference between rod 1 and rod 2, and rod 3 and rod 4 are almost equal to pi, 180 degree. And the phase difference between rod 2 and 3 is almost 0, which is a state of OM3. Hence, for alpha equal to 1, we experimentally obtain the output mode of vibration, which is OM3. And for all other alpha values, the state is either a two non-separable phi bit or two non-separable phi trits. To better visualize such non-separable state, in this couple of slides, I will show the eigenmode superpositions in terms of the pseudo-spin states of the elastic waves, which means in terms of the wave number K. To experimentally map the pseudo-spin states for the isofrequency value of 56.6 kHz, we choose different values of alpha, and using full field scanning laser vibrometer, we map the longitudinal modes elastic field for each of the alpha values. For example, when alpha equal to 0, we obtain these experimental results. This animation shows the experimental velocity field along the length of the first rod in the transverse direction, which match the elastic field of longitudinal modes. And in this plot, I am showing two snapshots from this animation of the spatial waveform for time t1 and time t2, which clearly shows the standing wave mode. Next, we perform the Fourier transform in space, which reveals the wave numbers associated with each mode of oscillations, hence reveals the state of the elastic waves. However, due to the finite length of our acoustic waveguide that only supports standing wave mode, we assume that the wavelength are multiples of 2L, where L is the length of the acoustic waveguides. Hence, we assume that wave number k times 2L is an integer. And let's assume k times 2L equal to k star. We perform the Fourier transform in space for this special waveform for alpha equal to 0, and we obtain these results. And again, in this plot, x-axis is the wave number, k star, and y-axis is the amplitude. If we see from this figure, for alpha equal to 1, we obtain that k star equal to 12 has the highest amplitude. Moreover, for the isofrequency value of 56.6 kHz, k star equal to 12 corresponds to OM4. Hence, when alpha equal to 0, the output mode of vibration is almost purely OM4, which is a separable state. Next, we perform the experiment for different values of alpha, say alpha equal to 0.5, and we obtain this Fourier transform in space of the spatial waveform. And from this plot, we see that when alpha equal to 0.5, the amplitudes of 13, 14, and 15 has the highest values. Moreover, for the isofrequency value of 56.6 kHz, k star equal to 13 corresponds to OM3, and k star equal to 14 and 15 corresponds to OM2. Hence, when alpha equal to 0.5, it's a state of two non-separable phi bits, which corresponds to OM2 and 3, and the pseudo spin corresponds to K2 and K3. And finally, for alpha equal to 0.75, we see that the amplitudes of 11, 12, k star equal to 11, 12, 13, and 14 has the highest amplitude. And again, for the isofrequency value of 56.6 kHz, k star equal to 11 and 12 corresponds to OM4, and k star equal to 13 corresponds to OM3, and k star equal to 14 corresponds to OM2. Therefore, alpha equal to 0.75 is a state of two non-separable phi treats. The first phi treat being the orbital angular momentum degrees of freedom 2, 3, and 4, and the second phi treat is the pseudo spin states labeled by K2, K3, and K4. And in summary, we have shown the theoretical requirements for realizing an elastic pseudo spin in an acoustic waveguide, and I have shown that the dispersion relation with cutoff frequency is a state that exhibits coherent superpositions of elastic waves propagating in opposite directions. Then we have experimentally demonstrated the existence of coherent superpositions of elastic wave states by the signature of cutoff frequency in the band structure. We have also shown the theoretical requirements for the creation of non-separable Bell states of either two phi bits or two phi treats. And finally, by choosing an isofrequency state and then by manipulating the excitation amplitude ratio, we are able to tune the Bell states Hilbert space. We are able to navigate the Bell states Hilbert space experimentally. The significance of our work is that our work steps toward implementing classical elastic systems, which are analogous to quantum systems. The experimental demonstration of the acoustic Bell state opens the door to the extension of the notion of classical non-separability to the emerging field of phononics. Our quantum analogs may exhibit the properties of quantum systems, which, without some of the drawbacks associated with the quantum systems like wave function collapse, or there is no wave function collapse for us, or there is no decoherence. And finally, we can use our entangled states to manipulate. We can use our entangled states to develop algorithms. And finally, I would like to thank our financial support, the Keck Foundation and the University of Arizona. And thank you for listening.
Thank you for